Perfect. So in the last session, I think we have tried to see all types of various file format. Maybe Praveen, you were not there, but what we have done, we have seen the Avro Parquet. If there's any question, you can ask. Otherwise, we can also take that up towards the end of the class. So that
Sure. Yeah.
yeah,
Yeah.
perfect. So this is how we have started. We understood the drawback of other processing engine of processing data processing engine of the Hadoop framework like MapReduce, Hive. They all have the limitation around the read and write. So we came up with in-memory processing, and in-memory processing was had some challenges, which was covered by Spark, and Spark gave us the framework uh, which it takes care of the in-memory processing capability, for which the immutability is required, lazy loading is required because you can't keep everything onto the memory all the time. So you have to bring it to the memory, process it, and then dump it. And then framework, the Spark framework is vast enough, which gives with the time it has uh, from RDD. I mean, it has evolved from RDD to data frame to dataset. Now there's a straightforward Spark SQL, so you can write to Spark SQL. Then it also gives you the streaming engine. So if you have Kafka or Kinesis or Event Hub in where live data is coming, live events are coming, you can process it within seconds, and then reply back to the, I mean, you can send the response back. Then the machine learning, which is again evolving these days, not these days, but from a couple of years. So machine learning framework on distributed platform is one of the great offering of Spark, because Python had the limitation that it can uh, process the data only with the memory which is available on one compute device. So one VM, one laptop, etc. PySpark give you the distributed processing, but Python itself doesn't give you. So if there is any library, if there is any machine learning libraries like Scikit and etc., or let's say CatBoost, they just run with one of the compute power of the machine. So how they have evolved, they have given you the GPU level of processing or TPU level of processing, and that's a different uh, game. But distributed parallel processing machine learning library is one of the great offering of Spark. Okay, graph processing is the another aspect, and we haven't spoken about a lot on the graph because we'll not touch this subject. Uh, this is completely into a different use case where you're working with the maps, or you have some salesman problem, node and vertices related stuff like LinkedIn, networking, etc. So some of the great use cases of GraphX are mapping. You can also check on the Google salesman problem, or greedy algorithm, or the networking, like how the LinkedIn connect one person to another person, and then another person to another person based on the uh, uh, company linkage. So those sort of requirement, if you, unless you have that sort of requirement, like how Facebook generate a graph of the users, and how LinkedIn generates a graph of your company profile and then connects all the users, unless you have that specific set of requirement where you want to create a generate a graph, ideally graph processing is not needed. So we'll not talk about this a lot. Coming to the anatomy of how the job runs, the application is at the top level. You create a Spark job. So what you write gets converted into the job, and when you do the Spark submit, you submit the job, which gets further converted into the multiple stages, and every stage is converted into the multiple task. Okay, so now that there is a in this slide, I think we have seen this structure earlier. that we have the driver and worker node, master and slave pattern, driver and executor pattern. They are all the same. So, and we have also seen that the Spark has its own cluster. It can also run on the Hadoop Yarn. It can also run on the Kubernetes Mesos, etc. So whosoever resource negotiator can be, cluster manager can be anyone, and it can be Spark by himself as well. So Spark can also do the cluster management. You can use Yarn, you can use Mesos, anything. Okay, now this is a simple uh, latency numbers. So let's say we are saying that the Spark is fast, but how fast? That's very important, right? So there's three things which is technically involved when we talk about data processing. If the data is available in the memory, it will be fastest. If the data is available on disk, it will be slow. And then if the data is available on a different disk and the network is involved, so network has its own bandwidth, right? 10 Gbps, 100 Gbps, 1000 Gbps, and etc. And unlimited Gbps. Gbps is like gigabit per second. So the transfer rate between the two disks. So like internet, when I ask for when I download something, data which is sitting on the remote machine comes through the wire, and maybe if I'm downloading something from US, it will come through all the way from transatlantic cable, and then it will come to my computer. So this network travel of data is something considered as very slow, because data is sitting somewhere and you are bringing it to your computer. So read time plus the travel time, which makes it very slow. So if you have to talk to an multiple worker nodes, and then they are not connected with the good network, then that could also be a problem. So transfer rate between one worker node to another worker node should be fast. Okay, so we understood memory is fastest, disk is slow. If the disk is local, if the if it's network, that means disk is remote. So you have the disk read time plus the network travel time. So that makes it slowest. Okay, so now let's say if everything is available in the data in the memory, and you are doing all the processing. So see what sort of numbers it looks like. So memory is further divided into L1 cache, L2 cache. So if everything is available on the recent, so you can consider it like hot, warm, and cold, even on the memory itself. So remember the processors. If you have studied the processor uh, earlier, that it has the memory registers, then it has the uh, easy access to the L1 cache, then there's slight latency added if you're reading from the L2 cache. So the instruction what you pass to the processor, it runs on the things available on the L1 cache, and after running that instruction, it will put it onto the L2. So things whatever is available on the L1, let's not go into that detail. The only thing we are trying to see here is that memory, the maximum time it's taking is like 100 nanoseconds. It's still nanosecond. Okay. Then over the disk, SSD read is 150 microseconds, and this is we are talking about in terms of 1 kilobyte data. Okay, 1 KB data in GP format. So if it's available in annual cache, it will take this seconds. It's available in this patch, this predictor, something. These are the different layers of the memory, and their timings. If you are sending 2K bytes over 1 Gbps network, it will take 20 microseconds. SSD read 1 MB sequential is like from hard disk, this seconds. And if you send one packet from Europe to US, 100 milliseconds. So there's a delay, right? We have just seen some numbers, so that if tomorrow we'll have to analyze that what volume of data we are reading from the disk and what volume of data is traveling, then we can make some projections that we need this. If we are doing a processing on 1000 GB of data, and we have memory of only 500 GB, and 500 GB is spilled to the disk. So what time will go towards the read of that one 500 GB data from the disk and 500 GB from the memory? So in the calculation, with reference to these number, you can understand. You can have some numbers that these many seconds it might take to process this amount of data. So this is just a reference, nothing much. The idea was that memory is fastest, disk is slow, and network is slowest. Then Spark context and Spark session. So we have talked about it earlier briefly, that initially when the Spark 1 or 2, there was a Spark context. We were creating the Spark context. Now we are just creating the Spark session, which is like a wrapper of dataset and data frame API. So it's more enhanced. And Spark context was like primarily working on RDD, so they created a new engine which converts your dataset and data frame. So we have seen that, right? We had the RDD, which is JSON-like structure, concurrent hash map, and then how the tabular data is getting represented to the RDD. So for all these things, the wrapper is needed. Finally, when the Spark was mature, it said that let's just work with a session, no context, and no need to. You don't have to worry about what's happening underneath with the RDD. So high level session is given. So Spark session consists of so if anytime in the during the if somebody will ask you this question, that Spark context and Spark session, what's the difference? It's the primary difference is that Spark session is an latest wrapper which gives us the session on which you can write your code, and it includes the dataset and data frame API. So it's an advanced version, including all the functionality of what Spark context was giving, Hive context was giving, and the SQL context was giving. SQL context was giving you the option to write SQL queries. Spark context was giving you the option to write all those Spark select, filter, map, reduce, etc. So Spark session is it's obviously the entry point. The first thing we do, I think during the practice session, we have seen that the first thing we do, that the Spark session dot builder dot local, and then we set the masters, and then we do the get or create. So we get the session, and then on that Spark session we start writing the code. So we do the Spark dot read CSV, or that Spark object is a Spark session object. And the point is, why we create a Spark session is because from that time onwards, Spark will start generating the diagram for you. It will generate a plan how your query will be executed. So it will start creating all the stages and tasks for you when you do the submit. So a Spark session is a Spark session will generate the diagram for your query execution plan, and it's a high level wrapper which gives you also all the functions of dataset and data frame API. Clear? Okay.
Yeah.
Now I think this we have seen the physical representation. If you will open that class RDD. RDD is an implementation like we saw, right? In Java we had the map, we had the concurrent hash map, and concurrent hash map implementation also you can see. RDD implementation, if you will see these many functions were written there: map, flat map, filter, reduce, fold, and aggregate. And that's the reason why when you do the something like this kind of program. You read some CSV file and do a word count. You first map those files. You first flatten it. I mean, all the lines gets in one line. Then you split it word by word. You will count it and then reduce everything. So these functions are written under the RDD. Now this could be one of the question in terms of the RDD. What are the ways to create the RDD? How many ways it can be created? So you can create simply by parallelizing it. So let's say if I think this also we have seen, right? We had the JSON, and if JSON you want to parallelize, that means if let's open that for the simplicity. Okay, so if this was your JSON and you call the parallelize, then maybe this will this looks like one object, but let's consider this is a list of millions of objects. Okay, so it's not getting over here. It's like millions of objects you have in the JSON. So let's say these many when you call the parallelize, these object will be created as one partition. These many MBs, will be created another partition, and every partition will be sent to the different worker nodes. So your RDD is your distributed data frame is created now. Your distributed you can also, when you read a text file on the Spark context, the RDD gets created. You can also just do I mean, you have created one RDD. From that RDD you can also create another RDD. So there's three ways, but I mean this is only from the interview perspective. RDD, this way of writing Spark code, it's something we don't do these days, right? We just do Spark. We create the Spark session. Instead of creating the Spark context, we create the Spark session and then we do the read CSV. We don't read it like a file and then RDD gets created and RDD gets distributed, and we do something like map or reduce or something. Rather, we just start writing the spark.sql and SQL queries. So that's an enhanced way, but you should know underneath what's happening, since we have already covered starting from the basic. So the question is, how many ways the RDD can be created? Three different ways. You can parallelize it. Parallelization means you are distributing a big JSON file. You are splitting that big JSON file into multi parts, and every part goes to the different worker nodes. So if there is a big 300 MB, let's say GB, if there is a 300 GB data set in JSON format, 100 GB will go to the one disk, 100 GB will go to the another worker node, 100 GB will go to the another worker node. So it's parallelized now, and all the references is sent to the cluster manager. So when we call parallelize, data gets distributed and their entries is being done by the done in the cluster manager. So cluster will know that what partition is stored at in which worker node or which executor. So from now onwards, we will call executor, because executor is something a Spark standard. Like when we say executors, we understand that we are talking about worker node of a Spark, and when we say Spark driver, a Spark driver is driver. So okay, then we have seen the actions and transformations. Like as long as we are calling map, flat map, and group by, Spark doesn't do anything. because you have to call an action to it, like count, collect, for each, take, reduce, save as text file, save as sequence file, or save, less. You have to call some action so that Spark will bring that data to the memory, process it, and then gives you the result and saves it to the disk. So it will clear the memory. It will just bring the data, process it, and clear the memory. Okay. So typically, I think we had seen, but let's draw it again. So if let's say you had not worker nodes, executors. If you had 3 executors. So 3 executors, let's say, collectively had 300 GB of process, 300 GB of memory. Collectively, let's say 3 compute device has this memory. This is the memory. So when you created the Spark session, you have written, let's say, select, filter, join, count, etc. Let's say you are doing these 4 operations, which is like select some rows, then filter the rows. Select when we do select, we select columns. So we have selected some columns. When we do filter, we filter rows. So we have filtered then some rows. So data is further limited. This was the data set, let's say. So when we did select, we selected only, let's say, these 2 columns. And when we applied filter, let's say we have filtered only these 2 rows. Only these 2 rows. So now this is your data. This is the only data set. So this was the big data set on which you got only the chunk of this, right? By doing the select and the filter. Then you do the join. You join this data set with some other data. And then let's say you apply some aggregation. A basic, let's say you are doing these 5 operations. So these are still your transformations. After so you can you will first read, select, filter, join, aggregation. You do all these operations. Spark will just keep on creating the graph for you. So Spark will continue creating the graph. Like, okay, so this is a acyclic graph, and then further it will either go save and then destroy this graph when the processing is done. So Spark session will start creating the graph for your query execution plan. And then when you call the save this file or show or whatever you are doing, then it will show the structure, destroy this graph, and clear your memory, clear this memory. So the data set for this is loaded here. All these actions are performed, and once you call the save method, it will be saved to the data will be 300 GB will be processed, and let's say 100 after processing 100 GB data is written, and then this will be cleared off. Spark will again, it will be available for the next processing. So this is what we are saying here, and we have there are some synonyms to it. So we are calling transformation and actions. Somebody calls transformers and accessors. Some calls mappers or reducers. Lazy functions and eager functions. So all the reducers are eager function, because when you call it, it just start doing the actions. So it's eagerly doing something, and all the transformations are lazy. So these are the synonyms. So if somebody asks what are the transformers and accessors in the Spark, that means you have to say these things. filter, select, join, aggregation, they are transformations. When you call save, collect, for each, etc., these are the accessors or reducers or eager functions. Okay, so till this point. Next is caching and persistence. So now let's talk about a complex query executions. In, let's say, you have this join. Let's say you have a big two big table join. I will just set the context here because this is very important to understand. Two big table join. If you this is a very complex thing in the Spark to be optimized and to be taken care. If there's two big table which needs to be joined and processed in this memory, that means it will obviously it will not fit, so it will spill and then it will crash, and then it could have different problems. So you have to handle it. How will you handle it? For those things, there is a caching and persistence strategy. Let's say you have processed some data. So what you will do, you will just save it, save it, or you will just put a checkpoint there, or so that your previous processing is not lost. Now you will do your you will process something, you will save that, you will process next and save that, so that you can process the complex query. So now Spark is taking care, and you are also instructing Spark to do it this way, do it your way, so that something which Spark cannot fit into the memory will do based on your instructions. And you will pass those instructions by knowing that this is the data set, how much we can cache, how much we can persist. Okay. And persist means persisting into the some permanent storage. I mean, mostly it's disk oriented. I mean, when you call save, what happens? That data from memory goes and resides in your hard disk, written onto your hard disk. And that hard disk is like distributed file system of Hadoop. So, but it went on to the storage, magnetic storage. Fair enough. So, on this slide, any question? Definition wise, this is a sweet and short definition. RDD. What is RDD? A group of partitions. Like, of course, the full form is resilient distributed data set. Distributed because it's shared across multiple executors. Resilient because Spark gives us the fault tolerance, that it's immutable, it's lazy, so that you will not lose the your processing. And technically, it holds not the complete data set. Even if you load 1 MB of data set, Spark will, and you have 3 executors, Spark will distribute it into 3 split of 1 MB file. So sometimes processing small file on Spark also takes few seconds, and processing big file also takes few seconds, because it tries to distribute it, and then the data travels across the network, and etc happens. So distribution, processing, collecting, even if it's a small data set, it takes sometimes similar amount of time. So in that case, what you can do, you can just restrict it, that do the processing on only on one executor. But if you don't do that changes, it will split it, and then it might take some time. It might take the similar time to process 1 MB of data or 1 GB of data. Sometimes it could happen based on your okay. So you have this function to control the partition size, what size you want to keep the each partitions. And let's say if it's a 1 MB file, and your partition size is 1 GB, then obviously it will just reside on one executor and it will run perfectly. But if your partition size is 64 KB, then 64 KB is distributed across 10 worker node. So partition size is a externally configurable value which decides that what volume of data you are processing based on how many executors you have. And yes, that's all. On this slide, any question? No?
No.
All right. Okay, so this is again hands-on with the RDD, which is just showing us the way how we create, but that's maybe we can hold it for the time because we have already seen the hands-on, and we have seen how to write with the Spark SQL and read CSV and do all these filter map and etc. etc.
Keshav,
Yes.
can you can we have the hands-on now? This one, can we execute this?
This Spark RDD functions.
Yeah, yeah.
Okay, so we can start the community data break. I think this is the first day, and cluster I have already started. Okay, so let's go. So 7th, 8th, 7th. And that was a Scala code. Okay, so let's write this Scala code. This one first is the val array. Val is like immutable variable in Scala is called val. So I'll just create a and I won't type that long structure. Rather, I will just write Spark is a processing engine. So array, I think it's is a processing engine. Is it okay? Yeah. So let's say this is our to start with data set. So now we'll write the Spark context. So to start the Spark context, let me just go to the GitHub. This is Spark Scala session. Okay, so this is not creating the Spark context, but we will do what we will do. We'll create the Spark context. Actually, we want to see the Spark context or Spark. Spark. Let's context. Let me see if I have any program with the Spark context. This is also a Spark session. Okay, so all are with the Spark sessions, but let's see. Spark equals to Spark context. Hello.
Yeah.
Yeah.
So till what time, till what point I was there with you all? I don't know when it got disconnected.
You were showing the Spark session and all. You were showing the GitHub link.
Okay, I was showing the GitHub link.
Yeah.
So they are all, I mean, on the GitHub, what I have on the GitHub, they are all using this Spark session. So but in this we are using the Spark context. So let's do one thing. Let's just see how to start the Spark context. Spark context object example. In a scalar. Get or create a Spark conf. Okay. So first I need to we are all in the meeting, right? Okay. So you have like in the Spark session, what we are doing same thing earlier. The point was like we were creating the Spark configuration, and the Spark configuration we are passing to the Spark context, and then on the Spark context we start writing the program. Now these things got summarized, so it was good to see the difference. Now you just simply do the Spark Session Builder. You provide your app name if you want, or masters local and get or create. So master is local. Instead of local, you can also do the star. I mean, star is like using all CPUs. One is like using one CPU. Okay, let's run this. Spark conf is not found. So do we need to import? Let's import push. Let's see what they have imported. Or I can see it here. Use the Apache. Everything. Let's check one more time. These things should be ideally available, but I think Databricks, the version of Spark, but yeah, the backward supportability should be there, right? So when running, the Spark context was created at should utilize the shared Spark context instead of creating one using the constructor in Scala Python. In shared Spark context can be accessed as SC. Okay, so what Databricks is saying is that you don't need to create a Spark context. Rather, you can just start using SC. It's already created for you. So I can just write a val and text file equals to sc dot and read should be available. Okay, so it's already available. Text c dot text file. Okay, so in over here it's already available, but we need to see this, right? So in order to see this, let's start this is the way to create the Spark context. And so let's keep this for the sample. What we have created one array, small array, right? A short one, and we know that we can also create the RDD using the parallelize. So let's use the parallelize function and pass this array. Okay, so Spark RDD is now created. So when we parallel now I think we have just written this. So what we can do, we'll see these functions now. We'll see map, flat map, filter, and etc. So first what we are doing, we did the SC parallelize. Then we are doing the RDD, and then we are rocketing the element of every element in that array to split by the space. So let's do that. We should give some name. Let's give it map RDD. And then the text file we have created, text file dot map the element in this to element dot split by space. You don't have to write element is not doing anything, so you can also write e rocket e dot split by space, this, right? Split by space. Okay, so see, first RDD was this was the it was first RDD. Then we applied the map function, and split split entire text in the space. So map function is applied. Next is we are doing the collect. So I think collect will just execute this operation. So we can call this directly on the map rdd dot collect. Okay, so Spark is there. There's a space is not a. It has done. It has created the map of. So we had this. This text has 1, 2, 3, 4 space, and that's 4 spaces. Like so, it's a pretty simple. Then we are doing. Okay, so there's a difference when we do the map and when we do the flat map. So I think now see the flat map RDD. What the flat map RDD is doing for us. Same thing. We are doing the flat, and we're doing a flat map here. And the syntax for the flat map is camel case. Okay, now collect this. So now see the difference. This map has created an array of strings. So this was an array of a string, right? It was an array which has I think he has also used this space and multiple strings, and then he has a split on that. So but we have provided a simple just this text. So let's to see the difference, like for them and with us, we can also provide in this way that just a second. Okay, so we'll just put some dummy more text here. Now say let's inline it, not needed. It's a array of string. This is the first string, this is second string, this is third string, right? Comma separated all the strings. Let's okay, so it's an array of a string. See this data structure here. Okay, now when I will parallelize this again. It was the first RDD. So it's asking me to change it. Sorry, illegal start of the definition. Okay, now remove this. I think in Scala we don't have the what we say that comment with the hash. In Python we put the hash and then do the comment, right? In Scala you can do this way, like this can be considered as a comment. This is multi-line comment. I on 7th. So, but wait. this was a multi-line comment, right? So why it has thrown the error? Not taking this also as a comment. Intelligent. Yes. Okay, so this is the way you can do the, I think in the Databricks as well. Okay, so now our map RDD is created. Now when I will try to collect the same, wait, it did with this array, we had the different array, right? Okay, so here text file 1. So let's run it again. Text file 1. Okay, now collect this. Okay, so see, now this is an array of strings. So this is an array, and the first array is the first string, second array is for the second string. So every string is like an array of strings, further strings. But this is fine. This is one string, this is another string, and then we have to split on this. Let's see the same thing what flat map does. So we also need to understand the difference between the map and the flat map. When we flatten, okay, over here text file 1. Okay, so see, when we flatten this structure, what it does, it just puts everything in one line. So now if I will have to count the number of words, I can count this space, and then it will give me the count of words, right? Every word is now separate. So I have flattened my data set. Let's say this would have been each string would have been a JSON, or each string would have been a different. So we could also try with the CSV. Instead of loading this array, we can read a CSV file over here, read text file, and then can further. So that also we can try. Let's first complete this, and then we'll load the CSV. So flat map, we have till flat map we have seen. I think over here it's doing with this array parallelize. Okay, so it's applying a filter. Filter is like doing the same thing. Over here we did the split. This is doing this. Map every element by 100, multiply map, and so okay, this is doing the same thing. It's just that within the same map, the only thing over here is the difference is that map partitions. So with map partitions, your RDD, this was the map RDD, and this was the map partition. So now we know that RDD is a group of partitions, right? And map partitions are a further group of those partitions. So let's see this maybe we can create this array and see this difference. Okay, array. Just a sec. we will do the same thing. So let's name it as RDD2 and SC dot. I was thinking to read this as a CSV. But okay, let's first complete this map partition part and then we'll do that. Then
Keshav, why this partition is happening? Like, what is the need of this? Like a flat map and map. Flat map. What is the need? What is the difference and where it is used? Like in which case it is used?
okay. So for this, that's a very important concept to understand. What is map and what is flat map? So I will start with the let's say you always have a data set, right? Over
Mm-hmm.
here we are taking simple data set, so it's also difficult. Sometimes it's also difficult for me to explain. This is like one-dimensional data set, and this is
Mm-hmm.
a text file, right? It's a very simple example. And you, despite you have seen, maybe this difference was not pretty much clear. So let's understand it from this perspective. What happened when we do the map and what happened when we do the flat map? Okay, so this is our data set. This is the column name. These are the various rows. Okay. So when we apply the map, conceptually, the structure of this will never change. Okay. So when we do the map operation, we had 4 columns. At the target end also we'll have the 4 columns. So first requirement for using the map is when you want to retain the same structure. Okay. Now what's the why we will need map? So you are mapping this to this, this to this. This goes here and this comes here. It's exact mapping. But during this map, let's say if this structure of this was let's say okay, let's say this C0. C0 was written in all a small case. Okay, it was all a small case. Let's use some. It was a small case. But at the target end, I want everything as an uppercase. Let's say even if this was a name as well. Name, I want to do uppercase operations. Over here, you want something like A, B, C, D in caps. So same data set has, okay, in map, first thing, the number of columns will remain the same. Okay. Second thing is you can apply the function to change the format of the rows. I mean, you can apply something. Let's say on C1 is numbers, right? So let's say I'm C1 multiplied by 2 is what I want to do. So this will become 2, this will become 4, this will become 6. So these kind of operations, if this is needed, you will do the map operation. And then if you want to apply a filter, so So a filter, let's say you just say that where C1 is C1 modulus is 0 or C1 modulus is 1, even number, odd numbers. You want to just keep the even numbers. Over here, only 1 and 3, you want to keep the even numbers. So 2 and 4 will come. I mean, let's apply the filter on C2. So on C2, the filter is applied for even number. Some calculation you have done. And so only the 6 and 8 has come. And these two record was removed. So map idea is to keep the structure same, but data set represent for that column could have a different format. So if it's a date time, you could have a different format for the date time. If this was a string here, you can convert it to the date. If this was a int here, you can convert it to the some other format, double or whatever you want. So this sort of transformation where row by row processing is happening and
Mm-hmm.
column remains the same. That's called the map operation. Okay. Now,
Mm-hmm.
when we flatten this, what will happen? So let's see the flat map for the same. Uh, so we had the same structure. Okay, one more, add it. Sorry, it was A, B, C, D, and rest. Let's say we'll leave it as it is. Okay, how it was, and then we are applying the flat map to this. Sorry. So when you flatten this, what will happen? Everything will go and flatten here. So this one box, let's say A, comma 1, 2, 1, 2. This was like this, right? So maybe I think this screen is smaller. Let's go. Okay. So this way we can at least represent 2 rows. 5, 6, 7, 8, 9, 10, 11, 12. So when we flatten this will become C0, C1, C2, C3, A 159, 159. So this is your row 1. Similarly, you will have the row 2. So this is this can have the this will have the same structure, but it will be like in one line you will get the entire data set splitted by some parameter. So what you're doing, you're flattening your map, and the structure will look like something. So there, let's say, let's put this, let's color this off, because this is a sort of separator. Okay, and the value over here will come as B, 2, 6, and 10. Okay, so flat map will just flatten your structure with in one line, so that your entire data set gets in can be read in one line, and then further you can apply the filter on this. So now it's easy for you to apply a filter on this, especially in the reducing operation. When you are reducing something, you can reduce it by this, that take this separator and count the values. So how many, whatever would be the number of the separator, that's the amount of values we have, right? So in flat map, okay, Now your question could be that what's the difference? I mean, can we not do the same? I mean, difference you have understood, but can we not do the same?
Keshav, I didn't get the last line. After applying filter in the flat map, what happens?
So this is let's say space. This is
Mm-hmm.
some sort of delimiter, right?
Mm-hmm.
It could be semicolon, it could be comma, it could be space, anything. So not the filter. I mean, when you do the count or aggregate and count this number of separators, it will give you the number of rows what we have.
Mm-hmm.
When we apply the filter, then again we will do the same thing. We'll apply a filter, like let's say on C2, we want only so you apply the filter on map or on the flat map, it will work as the same way. Like in the map, when you apply the filter on C2 equals to even, it just pick the C2 even values, right? So if I will apply this filter, then we will get only these C2 is even, so we'll get only 6 and 8. But over here, without applying the filter, you will get an array of 4 object,
Okay.
right? So one
Mm-hmm.
row is one object, and when you have flattened it, you got an array of that object, each object. So when you are applying the for each function, it becomes pretty handy. So flat map usage is like for when you apply the for each function, you want to do aggregation, you want to do the count. Count is also an aggregation, so no, not need to specify. But in these cases, flat map gives you row-wise separation, and it's just in one line. So it's a
Okay.
map of uh, that object. Sorry, it's an array of that object. It's an array of each row. And if row is a map, then that's it. But let's not complicate it. Just keep it as array of, and that's what we have seen in this example. So when we did the flat map,
And we cannot do any transformations when we are doing the flat map, applying the
no,
flat
we
map.
have
We
done
can
that
do.
transformation, right? We have done the
Okay,
split.
E split. Yeah.
Yeah. So every element wise, you can traverse. You can apply. I mean, I am doing the split, but you can do some other like in this operation. You will see that we are dividing it by 2, so that we will only get the so it's like absolute. When we divide every element by 2 and the remainder is 0, that means it's all even. So we'll get all the even numbers.
Yeah. The only way is how it returns the result is a different command.
Exactly. So a map has returned you the same object. You had a table, it has returned you a table. A flat map, when you gave a table, it returned you a array of rows. It has flattened it. You gave a text file. So let's say I will create a text file, or I would have some text file, right? Uh, let's create some text file. Okay, so this is a table, right? If I will put a comma, this can be a CSV file. This can be a text file. This can be anything. This is a perfect data set, a Tableau data set. or is this doesn't look like a data set? Let me know. If not, then I can go back to that listing whatever we have downloaded. But let's say this is a let's save this as a in this itself as a text file. Let's say Word and letters text. Now go back to our data. Okay, so where did I save it? This is under data engineering, data beacon words later. Okay, let's leave all this. I just wanted this thing, and I'll go back to our previous day 7 file. Okay, this was our day 7 file. Now let's RDD text and letters. Okay, so we have read this text file. RDD is created. Now let's do the map and the flat map, and then we'll try to do some operation on that. So map. Let's copy this so that RDB equals to dot map. So with the space. Okay, so that's the difference. In Scala, you have to give the val or var. If it this would have been the Python, you don't need. Python is further more enhanced and doesn't don't even need this val or var. So that's fine. This time we are using a Scala. They are almost the same. So now collect this. So see our array of strings means a table. This is structure. This is a string. This is a string, and this is one array. This is another array. This is another array. This is another array. So this is an array of strings, right? Array of strings. This is still not flattened. Instead of array of strings, we could also do a array of strings, right? So that's what the flat map does. If I need to do a count on this, I have to get this element. I have to iterate further. That I will get this element, then count how many strings we have. So let's say word count program. If I'll do on the map, I will have to write a for loop on this array, get this element, and in this element I will count 1, 2, 3, 4. Then I will go to this array. I will count. I have 5. In this element I will go. So I will go element wise, and then I will count, and then further I will sum. Instead, if I'll do flat, I'll just get an array, and I can just do a count of this, and then I'll get the. So that's a one simple word count example. So let's do that. Get this RTD. So this is the difference. This is we have just got the we have just flattened the one layer of it. Rest of the operation. So now it will be very easy if I'm counting. I'm aggregating. I'll just do a count of this, and I will get the how many words we have.
But if we want to fetch details of second row like that, how we can differentiate in the flat map?
So the array second index.
Okay.
I mean, how you access from an array. Same way. Let's say if I have to get this element, array index. It's a scalar starts from 1. Python starts from 0. So sorry, Python starts from 1. Scalar starts from 0. So 0, 1, 2, 3. 0, 1, 2. Second index. I need to get. Not clear.
Yeah, like in a map function, we have like if we have employee one and his salary details, and second row we have employee two details. So when the flat map, when we apply like that, we cannot differentiate, right? Like, it will just put everything in just one line. Is there any advantage of flat map over map?
Okay, so I think that we were discussing the advantage, but if it looks like this is still not clear, so we'll have to see some more use case so that you can further understand the reasoning behind the flat map. Is that so? How can I can understand? Because
Yeah.
map, as long as I see. Uh, let's again describe it. Flat map is a flattened structure of the map. Okay,
Mhm.
map is a collection, like it looks like a key value, and
Yeah.
then uh, I'll go back to this diagram. So in all general cases, technically you do you will keep those if you don't have a requirement to alter the structure column wise, you will keep the you will do the map operation. You will reduce the uh, uh, rows by applying filter, but map will keep the structures as it is, and row wise like small case uppercase operations are needed, you will do that simply using the map. You don't have to flatten it. Now, if you are doing the aggregation, then flattening this will give you an advantage because uh, you can do a count, max, min operation in that in from a simple array structure. Working on an array is simpler than working on a map. So one of the advantages which comes, to my mind is uh, if you don't, you are not doing the immediate aggregation. You are just doing the join operation, or you are just going to next perform the filter operation. You will continue with the doing the map. You are not changing the structure. You are just changing the row format. You have converted the date time to a string to date time. The entering structure, not the physical structure of the data set. You will do the map operation. Now, if you do the next step is to perform aggregation function. Then you will flatten the structure so that you can perform the aggregation better. or quick. So
Yeah,
any reduced
got it.
operation, if the reduced operation is the next thing you are doing, you'll go with the flat map. So
Yeah, got
that's the only difference. But I still have a doubt that you are clear on this. But let's take some examples so that it get further. Uh,
Okay, sure. I think I'm clear on this now.
you're clear. So
Yeah.
okay, let's take some more example. Uh, okay, so in this, what we are doing, we have filtered it. We have after filtering, uh, we have done the map. But this is applied on the RDD. So that's why it has all the rules. But if we will apply it on the filter RDD, let's try this. So we have this array. Is not equal to 2, is not equals to 2. Simple. Then on this filter val map filter RDD, then filter RDD. So first we need to see this as well, right? This filter RDD has what? Filter collect not equals to 2. So I think only the 2 has been. Why not use something like even or odd? But that's fine. 2 is removed from this array. 2 is removed, and we have rest of the element. On rest of the element, let's apply the map. So now do the map operation. So on this, what can we do? We don't have to split on row error. We don't have to. Uh, how we can split this? What other functions we can apply? E equals to B divided by 2. So what it will do? It will just multiply each element by 2, but we'll have the same number of elements. The number of elements has not changed. But this was one dimensional, so you didn't see that the structure change. With the 2 dimension, you are seeing this structure change here. This was 2 dimensions, so we split on this. Now let's say let's split on new line character, and what happens? So still the structure is array of the strings. You do the split on the new line or on the space. I mean, it's still the same. The same point what I was trying to say, that one layer, when you are flattening it, you are just getting the you have flattened the structure, so you have got the next element, and the operating on this is easier than operating on this, because this is an array of a string, so you'll have to apply a for loop here. And to remove that cost of for loop, flat map, I think internally have written, let's see the implementation of flat map. What is the flat map implementation in RDD object? No, Spark RDD. I think I want to see the source code. RDD Java source code. I think we had this right. Abstract class RDD implementation. Abstract class RDD source code. Yeah, this is the one. Okay, so in the RDD, the flat map function is written. It's a traversable once, and the it's traversing the inner object. What I want to see is the code. Oh, abstract class RDD implementation. Okay, anyways, I will it says that the flat map is traversing within the element of this U, the map. So and we have seen this here. If this is still not clear, maybe we will revisit this. I will keep that thing some easy to understand example ready, and then we'll revisit this. Okay. All right. This part is done now. Okay, I have a link here. What this link says. Maybe some more definition would be there. Oh, I think this is the same. Yeah, it's the same thing. He's also over here also we're trying to explain the same stuff. Flat map transformation can give many outputs to the RDD. Map and flat map are similar in the way they take a line from input RDD and apply a function on that line. And the key difference is between the map and the flat map is that is a map return only one element, flat map return a list of element. So I don't know. This makes more sense, or flat map returns, in fact, a lower level of structure. So if your map was an array of a string, flat map will return array of a string. If your map was a map of array of a string, then it will return also the array of a string. It will return a layer down. Okay. So I can share this link. And you can go through this. All right, coming back to our next stuff. Fold and reduce operation. We have I think I would also so see over here we are seeing again an interview question which is like in Spark we have reduced by key, group by key, aggregate by key, combine by key. There are a couple of ways, like in SQL we write simply, right, group by and this, and then we never understand what happens underneath. But Spark has I mean, group by I think we understand, right? When we apply a group by on a table, similar same key gets collected together. So if name, simple example, and then mf mf. So when we do aggregation on this, let's say group by we are doing by mail, so we'll see only this structure, right? And then we'll see the count here. So aggregation, what it is, it groups the same element. It gives us the male count and female count total in that data set. So but this thing to happen on Spark, it becomes difficult. Why? Because this is your complete data set, and this will get further split into maybe this way. One executor will get this data, and remove this. Let's distribute. Another executor no. Okay, so on this is a table, and on this table, when we write select count star gender from this table, group by gender, we get male, female, and then we get the count of it. So total 1, 2, and 1, 2, 3, 4, 5, 6. So 2 and 6. This we will get right in the normal database if we will do this operation. And when I say normal database, that means a relational database, and where entire data set can be stored on. So in Oracle, there was a vertical, right? So everything was being processed as a one structure. But Spark does the processing on the big data, and then this let's consider this as a huge data. So this got split into the further two things. So if I will do a group by operation on this, I will get this count, right? There is 2 and there is 2. So this on this from this executor we'll get this result. Oh, sorry, not the merge. And from this executor we'll get 0, and this is as 4. And then these two will get further clubbed on the driver, and then the count final answer would be 2 and f equals to 6, right? This should be the final answer. Spark does the processing in over the executors. So when it does the group by function, the data is grouped on every node and then passed on. So that's one of the way. Wait. The difference in when we do the group by and reduce by, let me, somewhere it should be, we'll execute and see the difference. But okay, no, it's here, right? So when we do the group by, okay, leave the combiner concept. There is okay, to establish this point, there could be this could be done in two ways, right? When we do the group by key, this is equally important like map and flat map, and one of the good interview questions. And when we do the reduce by key, sorry, reduce by group by key, okay. So when we do the group by key, what happens? All the key was like gender, right? So all the gender from this and this will be read. So from this, all the male will be collected, and from this, all the female will be collected. So when we'll do the group by key, Spark will do the shuffling. Okay, so how this okay, first understand that this is the this what we have seen is a reduce by key. So on every executor we have reduced by key, and then we have further collected the answer. So this was an effective operation, right? Every executor has the data set. Let's get the let's reduce on that executor itself, and reduce data will get to travel over the network. Okay, so this data got reduced in this data got reduced in this way, and this data was sent to the and then this data was only traveling over the network. So network latency was less in case of reduced by operation. So reduced by operation is fast, but when we do group by, what happens that we still have the two executor, and on this executor Spark will do the internal shuffling and see the problem. Spark will call all the key what you have, you return. So this will return all this data set, this data set, this data set. So and this will have this data set. Okay, so in group by operation, this will happen. Spark will call out the key from every that you have. Okay, how many keys we have, and then based on every key, let's say if this would have been the five different values or 10 different values, then how it will do, we'll see the hashing and etc. But in simple way, if there was two executor and there was two key, this is how it will work. So entire data will be called to the master again, and master will redistribute the data. So it will shuffle the data again. So shuffling will add some time, and then the data will be distributed again. So shuffling, and then so what will be returned from this? The m equals to 2 will come from here, and f equals to 6 will come from here, and then we'll get this answer. So where is the shape? So see which one this is clear, right? You saw the difference why group by is slow, because group by tried to shuffle the structure of the data set again when on all the executor, and every executor had the similar keys. So this is a simple way to establish the point why group by key is slow. Now the question comes that let's say we have only 5 executor and there are 15 keys. So what will happen? In that case also Spark will call, and then maybe 5 keys will go to this and 5 keys will go to this. So let's say we have 10 keys and we have 2 executors. So let's say we have a status like active, closed, pending, in progress. Let's say we have now 4 and we have only 2 executors. So and then the count is like 10, 20, 30, 40, let's say. So if this time we have written the query select star from state, this is a status, some sort of a different data set I'm talking about. So in this case Spark will do is in this case also Spark will call everything key wise to the master and then shuffle it again. So let's say active and close will go to this, active and close will come to this, and pending and progress will go here. And then From this, active and closed status will come. From this, pending and progress status will come. So lots. So again, data size was used. Lots of shuffling and sorting. So shuffle and sort, which happens on in case of the group by, that makes it slower, and reduce by key is faster. And okay, so till this point, is it clear?
Yeah, okay.
Okay, so then we have something called aggregate by key and combine by key. But aggregate by key also works similar to the reduce by key. It does in the same way. Combine by key uses a combiner, and combiner is something in between map and reduce. So in map and reduce operation, there is a combiner which improves the performance of map and reduce operation. So if you use the combine by key, Spark will further brings the take the advantage of the combiner and then do it. That will make a little more faster than the reduce by key. But implicit and explicit use of the combiner is the only difference between them. Okay, but reduce by key is technically faster than among others. Okay, now to understand this in more details, you can refer to this link. This is still not sent. Okay. So if you go to this link, you will get to read about them, and then you can correlate with this diagram. So I'll also snippet and then just put it for your reference. Okay, so this is covered now. Shuffling and partitioning. Now this is another example. Right now we have just seen how shuffling was a pain. So we'll see the shuffling and partitioning. Shuffling and partitioning is maybe we'll take this up tomorrow. Because this will if I will start this, I will again have to distribute the data and then establish this point. But this is a very important point, so we'll take this up tomorrow. Shuffle is normally we understand, right? Like card shuffle or everything shuffle. When we do shuffle, it's like we collect everything and then we start distributing that again. And Spark also has to do that because it's a big data, has to be processed among multiple executors, so it has to be shuffled and then distributed among all the executor in partitions. So how Spark does the shuffling and partitioning is will decide how you do your shuffling and partitioning. It will decide the performance of the Spark. So it's a very important from the concept perspective. So we'll see this in detail tomorrow. Okay.
Okay.
I think what else is after this? We will have data set and data frame we have covered. We have another one concept which is optimization, that we will see tomorrow. So technically most of the concept will be covered. and then we'll one by one go through what happens during the interviews. So two concepts, shuffling and partitioning, and optimization for two big tables, how that works. That the two concepts we will cover tomorrow. Okay, rest of the hands-on, I mean 7th day hands-on, I'll put it on the drive so you can practice it, and that's all. Now if you have any questions, tell me.